matters. Because technically we're both doing it, so I guess whoever gets, like, we'll just share the list with each other.
Yeah, that makes sense.
Okay.
So either one.
Okay, cool.
Okay, so
we are recording.
Yes.
Okay.
Let's see if it works.
Okay, I can see your screen.
Okay, let me stop sharing then and see if it works. Yay!
All right, and then let me see what happens if I do this. And oh my gosh, we did it. We did it.
I'm so proud of us.
Oh, you guys are just here watching us. Just be proud that we know how to use technology.
It's been like 7 weeks, but you know.
Hey, it's a little different with the two of us both having to do a session together, so I think we're doing a great job right now.
True. Especially after
guys.
Oh, go ahead.
Go ahead.
I was just going to say, especially after the first exam review train wreck that was happening.
The amount of times we had to pause just so we could get our stuff together, and then we just laugh for like 5 minutes straight, and then continue.
Yes.
Rosemary, did you put them so they're muted on entry, or do they need to self-mute?
Oh, what I realized is if I do mute on entry, they can't unmute themselves.
Okay. All right. So everybody just needs to mute themselves on entry then, right?
Yeah. And
okay, cool.
If they don't mute, I just mute them. And then if they ask me to unmute, then it might be more complicated that way, but they should.
Yeah, no, I get it. Okay.
What just?
Seems like people are starting to roll in. Do you want to do the Kahoot on my laptop or your laptop? It doesn't really matter to me.
You can do it on yours if you want.
Okay.
And then if it starts being weird or laggy or anything, we can just switch over.
Okay.
Cool. Okay, so you guys that are here, we still have like a couple minutes, so I want to show you the best thing I've ever purchased. And I'm gonna... Everyone's like, what? Hold on. I'm gonna make it dark for a second. All right. So I am obsessed with candles, and I'm also obsessed with brains, right? So
oh my gosh.
My amazement when I found this candle, it literally changes colors. Look!
That's so cool.
I am so happy. I literally am going to go back and buy like 40 more. It's the best thing I've ever purchased. Anywho's, you have to make my day.
Where did you buy it?
From Michael's.
Okay. Oh my gosh, was that Michael's?
Yeah, and they're like much bigger than I expected, and there's like a whole bunch of different stuff. So like there's one of the lungs, there's one of like a hand, there was one of like a bug, which I was like, that's kind of random, but I love it.
Okay. Rosemary, should I show them the kittens?
Yes!
Okay, I don't have any audio on my iPad, but I do have video sharing, so I'm going to stop my video here, and then you guys will just, like, hear me. Okay. I'm gonna flip this so you guys don't see my face. How do you flip a camera? Okay. Hold on, guys.
While she does that, I'll go get Bear. Because we're real professionals.
I just opened it for a second. Sorry.
Oh, they're fine.
They'll be fine. They'll go back to sleep.
It's Bear. Come here. Oh, come here. Oh, baby. Bear just took a shower and we blow dried him, so he's much fluffy. He says hi. Hi.
Yes, if you guys have puppies,
Yes,
feel free to share.
Everyone
Share the
show
puppy
your
love.
puppies. That's the true nature of this session.
Puppies are any animal, you know.
Yes.
We are animal lovers here.
Oh, look, Bear, it's a doggy. He's like, what are you saying to me, Mom? I don't get it. Ah, so many doggies.
Oh my gosh, yes.
Sea turtles.
Oh my God, baby turtles, baby turtles.
I literally just told her about the sea turtles. I was like,
She was literally just talking to me about that. Oh my gosh, Sean, your dog is just passed out. Me if I wasn't on coffee right now.
Bear is like, why won't you he's like, why won't you let me go sleep? Like, I don't understand.
Bear's just like, come on. I want to take a nap.
Yeah, he's so mad at me because I like blow dried him. Are you ready to go, baby? Say bye-bye. 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 I love you, Bear. Go. Go be free.
Okay, so we have more people joining in. I'm going to drop the sign-in link for this. You could either enter it, actually, for now, just everybody put that we're under, that the SI leader that you're under is Rosemary, just so we could keep it all on one sheet. So enter Rosemary.
Andrew is like, you lied to me.
Okay. I'm sorry. Okay. There we go. We should be good. So go ahead and enter that. We'll get started. Oh, we can get started right now. Do you want to get started, Rosemary, or do you want to give them another couple of minutes?
Yes. Let's wait like 1 more minute to get started.
Okay. Because it does seem like we still have a lot of people coming in.
Yeah. And I feel like we're going to have to keep sending the attendance thing, so I don't want to keep like pausing.
Guys, so the way we're going to try and run this is that Rosemary's going to do the first half of the concepts, and then I'll do the second half. So I will just be answering questions in the chat. So if you guys have any questions and you don't feel like unmuting yourself, I will try my best to get back to you as fast as possible in the chat. Or if it's a question that probably needs to be like answered by Rosemary herself, I'll just like I'll let Rosemary know what it says. So we don't have like 50 million people unmuting themselves when we're doing this.
Yes. And then also if I do this thing where I sometimes forget things instantly. So if you like see a question and then like I don't ever answer it, just let me know. I'm not old.
I have a question. Are we gonna go based on the practice problems that he posted for chapter 11, 12, and 13, or?
So we're gonna do concepts first. So we're just gonna run through the handout that I sent you guys, and we're gonna do all of the concepts in the first hour-ish. And then in the second hour, Katrina actually made like a practice exam Kahoot game that has a bunch of Dr. West's questions and some of our questions. So it's going to be both.
Oh, okay. When did you send it? I'm gonna print it before we start. I didn't see it.
Oh, yeah, no worries. I sent it after the weekly email, but I can go ahead and send it on Canvas super quick.
Perfect.
Let me drop that in an announcement for section 2 as well.
Oh, because we don't have access to everyone.
This stuff is so crazy.
I know.
Okay.
Okay,
All right.
so you guys can actually, we're gonna start in 2 minutes to make it like 5:05. So in the meantime, if you guys have any questions about the review or the exam or anything, feel free to either unmute or say it in the chat or whatever. You know the deal.
Oh my gosh, can I not? I can't send it to all the students in the course, Rosemary. I don't know why.
Yeah, he removed us from that. So now we have to do it just in our SI courses.
Okay, so you guys need to at least be enrolled in one of our SI courses.
Love it.
Unfortunately.
Unfortunately.
So,
he just sucks so bad, but...
Wait, so are you guys doing this together?
Yes,
yes, we're doing this together.
Oh, okay.
All right, so,
wait, can I not?
SI session, handout.
Oh, I can. Okay.
SI, let me put exam review.
Review. Someone is going to see this and be like, wait, where am I? What exam? And I feel that.
Okay, I am sending it now. It should be under, here.
No, what have I done?
Handout.
Okay, well, I sent the handout, but for some reason I also sent a video to you guys, but I don't know what that's about. I really don't.
Okay, so I just sent it to whoever's enrolled in my Canvas course as well, so.
Okay, so someone asked if I posted anything to the YouTube. Yes, I did. I posted Friday session, Monday session, and 2 other videos, and then I have to finish 2 more today. So we'll get to that. Someone said, do you have any tips
somebody
for
is asking for tips for cramming.
Do you have any?
Okay. I did like Rosemary's page for her very short YouTube videos. So if you do that, I think that'll help with some of it. But basically, my advice would be practice problems, just because I think practice problems is the best way to get used to his material. So go through the practice problems and try your best to do them. You can literally have the SI handout next to you while you're doing them if you don't know how the reaction mechanism takes place. But go do practice problems. That's all I can really say. And in regards to the Kahoot questions, all the questions that are on there are either concept ones that Rosemary and I came up with, or they're from the chapter 11 and 12 practice problems he posted, or it's in his lecture slides. I did not pull anything that is not in there. So you guys should have access to all of that.
Yep. One tip that I have that's kind of like a what not to do. Do not drink as much coffee as you think you need the night before the exam. Just trust me on that one.
And then there's me drinking coffee before I took an exam.
No, yeah. Coffee's great, just don't, like, die. All right, so I think it's pretty much a good time to get started. If anyone else comes in late, that's okay. So Katrina just sent the attendance link again, so if you haven't filled that out, please do so. And if there's no more questions, we're gonna...
I'm sorry, it's the one that says exam to review, right? Oh yeah, that one.
Yes.
Okay. Perfect.
Rosemary, there's a question asking about where they can get more practice problems if they already finished all the ones from the SI sheets and chapter problems.
Okay, so I would say, I'm sorry for bear barking in the background, by the way. Do the SI sheets and the ones on Canvas first, and then once you do those, you could always do like the textbook problems, or if you still have your ACS book from Orgo 1, I did those just for practice. But the most helpful ones are usually the ones that he posts on Canvas. I feel like I have a stroke saying that. Okay, cool.
All right.
So, time for the fun stuff, guys. I'm sorry if I'm screaming. I'm keeping all of us awake. So, the first thing we learned about was ethers. That's where we start chapter 11 for this exam. And we're learning mainly how to make and break ethers. Looking back at it now, I don't know why I put break instead of making, but I guess we'll roll with it. So, before we do anything, I'm going to just draw on the side what the general form of an ether is, and then what the general form of an epoxide is. So an ether is just an oxygen with 2 carbon groups or 2 R groups, and an epoxide is a cyclic ether with exactly 3 members in the ring. So 1, 2, 3, which means that it's attached to 2 carbons. Now, we have 2 main ways to break ethers and epoxides, and that would be acids and bases, right? So ethers, in general, are pretty stable, so they can only be cleaved in acid. They are stable in base. So, sorry, I'm on my eraser. And in the acid, as I told you guys, acids are a pain in the ass. So the number order is super weird. So it's 3, 1, 2. On the other hand, we have our epoxides, which are super, super, super unstable. So they always want to break no matter what you use. So they can actually be broken in the same order by acids, or in a base. Since bases are basic bitches, they go in the regular order that numbers go. And I'm sorry I keep stuttering. My dog is just distracting me. Any questions on breaking epoxides? This is essentially all you really need.
Yes. When you say base stable, what does that mean? Is there an order for that on the making ethers?
Good question. So all that means is that any ethers besides this specific cyclic ether will not be cleaved in base at all. So there will be no cleavage. And another thing to add to that, when I put this order of reactivity, I just want to note one more time that what we're talking about for order of reactivity is order of preferential attack. And what I mean by order of preferential attack is the order that the nucleophile prefers to attack. And we'll do some examples, so I don't want to spend too much time on that right now. But essentially, in an acid, the nucleophile will prefer to attack tertiary, and then primary, and then secondary. But then in a base, it would prefer primary, and then secondary, and then tertiary. So when we're making ethers and epoxides, we have our first reaction, which is called the Williamson ether synthesis. And that is essentially just when we react an alcohol, such as this one, with a base, such as this one. So we are going to steal that hydrogen and make the conjugate base of our alcohol. And it's important that you know that this conjugate base is called an alkoxide. And then you can react the alkoxide with an alkyl halide, such as, let's say, this. And when we attack, we kick off the leaving group, and now we have formed, sorry about that, an ether. And one thing I want to, this isn't finished drawing, by the way, because I want you guys to pay really close attention. So this is the first carbon. This bond gets kicked off. So when you're drawing your final product, make sure you have 1, 2, 3. So we have 1, 2, 3. So as far as epoxides go, we can do the Williamson ether synthesis, but we'll do the intramolecular. And I'm just going to say WES because I don't want to write out the whole thing again. So in the intramolecular Williamson ether, we are going to have our alcohol and our, sorry, I just realized it's taking so much time to write. It's fine. So our alcohol and our halogen must be on the same carbon chain, and we react it with a base such as this one again. And at this point, we will form the alkoxide. Bam. And then it will attack, kick off the leaving group, and form an epoxide. One thing I like to note is the way I draw epoxides is like this, where I leave the actual ring on the plane, and then I put the substituents as wedged or dashed. And the reason I do it that way is because this is pointing down, this is pointing up, so they are opposite to one another, so the product will be trans. And it just makes more sense visually if you have the ring on one plane.
Will the product always be trans?
Not necessarily. It just depends on how this is drawn. So, for example, you guys have seen, if you were in my SI sessions, that in order for this reaction to take place, the nucleophile, which is O-, and the leaving group have to be on opposite planes so that we can do a backside attack, right? So if this was like wedged or something and we had to rotate it so that it was, for some reason, I don't know, this is a really weird example, but right, so now they're cis to one another, so it would end up being the cis product. I don't know why you would do this, but it's possible.
Hey, Rosemary, so somebody was asking, is there inversion for Williamson ether synthesis? And I feel like that's a question that a lot of people might have, so if you want to,
Yes.
you know.
So that's a great question. Yes. So yes, but also we don't really look at the what do you call it? The stereochemistry for two things that are attached to the oxygen. So yes, since it's like an SN2 mechanism, it will flip. It'll do like a backside attack and kick that off. So it'll invert the stereochemistry, but that's not something you really have to be too stressed about in this case, because he won't like ask you to do like a stereochemistry for that, if that makes sense.
Just a question I had on the one earlier. Do we leave it as breaking ethers and breaking epoxides? Oh, you changed it. I'm sorry, because I was, oh, no, never mind. Do we leave it as that, as breaking ethers and breaking epoxides, or do we scratch it off and put making ethers and making epoxides?
So no, this one was breaking, and now we're doing making.
Okay, great.
I know I did it kind of backwards, and that was weird of me, but I like to make things complicated. And then someone said, is the H supposed to be... I don't know. I erased it. It was just supposed to be an H, but it's not like a big deal. Okay. And then someone asked, are you going to go over breaking reactions? Yes, we are. But I have some examples already written, so I didn't want to do it just then. We'll do it in like a second. So the second method of making epoxides is with a double bond and a peroxy acid. And it doesn't matter what peroxy acid you use. There are a bunch of different ones, and it's in the PowerPoint and the handout, like the usual handout that I do, and it's already drawn out, so I'm not going to spend time covering them and drawing them now. The one thing I want you guys to remember is O3 is indicative of a peroxy acid. So if you ever see O3 in a condensed formula, that means you're working with a peroxy acid. And that means that you will end up with an epoxide. And one thing that you should always note is if you're doing a double bond, you're always going to keep your configuration. So this is a more common case of having cis and trans epoxides. So in this case, they are trans, they're pointing opposite directions. So one side has to be wedged and one has to be dashed. But if we had the cis double bond and some peroxy acid, we would make a cis epoxide, like so. And it could be both wedged or both dashed. And that is pretty much it for making ethers and epoxides. So I'll zoom out a little bit so you guys can see both of the things we just did. And if you have any questions, let me know. I know someone unmuted to ask something. So if you want to ask. Okay, cool. So next thing is naming crown ethers. Honestly, this is one of those things that's like a really easy free gimme point. So we are essentially going to note that the larger number goes first, followed by crown, followed by the smaller number, ether. And so what that represents is the total number of members in the ring, crown, number of oxygens, ether. And the easiest way to do this is to first count the number of oxygens. So here we have 1, 2, 3, 4. You do 4 times 3, which is 12. So this would be 12 crown, 4 ether. Don't ask me why the times 3 rule always works, but for this class, it always does. So for the second one, we have 1, 2, 3, 4, 5, 6. 6 times 3 is 18. So we would have 18 crown, 6 ether. And just so you guys are prepared, a lot of the time on his exams, he'll just say like 18 crown 6 or 12 crown 4. So if there's no ether at the end, that's okay. You can either have it or not. It's not going to be like a wrong answer if he does it like that. And then someone asked in the chat that some of the Orion homework asks you to use crown ethers in the reaction, and will that be on the exam? No. I've literally never ever seen him talk about or put that on the exam. Sounds kind of awful. So now that we did the conceptual stuff, we're going to move on and do the reaction stuff. So the first 2 examples are examples of making ethers. And as we said before, we can start with an alcohol and react it with a base. And the base is going to deprotonate. And then we react it with the alkyl halide. And this forms an ether, so we draw the oxygen in the middle. On one side, we have 1, 2, 3 carbons. So 1, 2, 3. And on the other side, we're going to have 1, 2, 3 carbons again, but you're going to attack right here. So it's going to be 1, and then the branching. For the next one, we have our base again. So it's going to steal the deprotonate. And another name for this starting material is a halohydrin. And I know that was in some of his problems and people were getting confused because I didn't use that name. So just know that's what a halohydrin is. And so we're going to deprotonate, and then we're going to attack and kick off the leaving group. So you end up with an epoxide. Ta-da! We pretty much did these before, but just to reiterate, this one is the Williamson ether. It's the intermolecular. And then we have the intramolecular, which makes cyclic ethers. And sometimes it can make an epoxide. Any questions, comments, or concerns?
Yes. Could you please draw the arrows on that first reaction you did?
Yes. So I'm just gonna pretend that we already deprotonated, and this will come and attack and kick off the bromine.
Can you draw the arrows for everything? Like all the reactions?
Yes. So how about I can draw all the arrows that you guys need to know. Because there's some reactions that have like a really long mechanism, but you don't need to know it at all. Is that fair? I think it's fair.
Yeah, I understand.
Okay, cool. Because like the peroxy acid one, trust me, you don't want to see any kind of arrows. It's literally disgusting. And as we said, all we really need to worry about is peroxy acid and double bond, make an epoxide, and we know since the double bond is trans, we end up with trans substituents. So for this one, the first thing we're going to do is count the number of carbons. So 1, 2, 3, 4, 5. And it doesn't matter where you start. I just like to start from the oxygen side. And when we react with HBr, we know that the first step is going to be activation. So it's going to protonate. And after we protonate, we get this and a positive charge. So now it's a better leaving group. And we have Br minus, which is going to come into one of the sides and break this open, right? And since we have an acid catalyst, our order for attack is going to be 3, 1, 2. And we see that this side is secondary, while this side is primary. So the bromine will prefer, according to our list, to attack this side. And so that means we break this bond and open that way. So I'm going to draw my chain out first. And so this is carbon 1, 2, 3, 4, 5. I guess just kidding. There you go. And then off of carbon 5, we have an extra methyl. And on carbon 5, we also have our OH. I'm going to draw that in. And coming off of carbon 1, we have our nucleophile, which was bromine. Now, if we have excess HBr, all that means is we are going to take this first step, do exactly that, and then we are going to attack. Hold on, I'll copy this for you guys, just so you know that that's still the intermediate. And then at this point, you have extra HBr. So this will take a hydrogen, become H2O plus, and now that it's a good leaving group, our Br minus will come in and attack, kicking off the leaving group. And I'm gonna scoot this over, but then I'll zoom out at the end again. And we end up with 2 bromines on our final product. And so
Does
now,
this only apply?
oh, sorry, go ahead.
Does this only apply to halohydrons? Like when you have excess halohydrons, is that the only time you would do it? You would do that kind of mechanism?
So that would only be when you have excess acid and you're reacting it with a cyclic ether that's not an epoxide, if that makes sense.
Okay. Thank you.
You're very welcome. Wow, that was a voice crack and a half.
I'm sorry. In a halohydron, you said it's a halogen with the OH.
Yes.
Basically, that's what that is.
Yes. So the halohydron is just. Where did I? Oh wow, I'm dumb. So yeah, this is the halohydron. It's a carbon chain that has both an OH and a halogen. So someone was asking about stereochemistry. As far as this goes, they didn't start out with any stereochemistry, so don't worry about stereochemistry. Now we're going to do these 3, and they're so much fun because it's pretty much the same exact question that he can give you 100 different ways, and you will all get it right because you were here. So in the first example, we're going to react the epoxide in acid. And acid means that the order is 3, 1, 2. And so let's just look at the 2 sides of our epoxide. This one is primary because it only has 1 carbon attached. And this side is tertiary. And we know that since this is what they're showing us, that whatever is going to be attacking, aka the nucleophile, will look like so. And we can say that because acid prefers tertiary, we're going to attack this side. We're going to break this bond and open that way. So I will draw this out. And as I said, we are going to have our nucleophile, which is an OCH3, attach here. And we have 1, 2. Coming off of that, we have our O, which was an O minus, but it gets protonated to be an OH. Since they didn't give you any stereochemistry in the beginning, you wouldn't have to worry about stereochemistry for the product.
I have a quick question. Where did that oxygen ion come from?
Oh, this one right here?
Yeah. Mm-hmm.
So essentially, the oxygen in the ring is going to take the hydrogen to become protonated. But it could also attack as an OH. I just chose to draw it with the minus, so it makes more sense.
The oxygen in the ring, you mean which oxygen?
This one.
I'm confused.
So, okay. I probably should have drawn the first step first. So that's on me. You caught me slipping. So in the first state,
Please, thanks.
would actually be the activation step. So if we had CH3OH, like so, this oxygen in the epoxide will take the hydrogen and give those electrons to the oxygen, which would make this. And now the nucleophile has a negative charge because it lost that extra hydrogen. I should have probably drawn it in. So that's my bad. I'm sorry I confused you, but does this make more sense?
That makes a lot more sense.
Okay, good.
I have a question.
Yes.
Is this one of the mechanisms that we would need to know the arrows for? Or is it one of like those, just know the product?
Just know the product. The only reason I'm drawing the arrows is so that you guys can see like acid prefers what side versus base prefers what side. But you definitely don't need to know it.
Okay. Okay, so the only ones we really need to know like the mechanisms for is like which ones?
I mean, let me be honest. You're not going to have to reproduce a mechanism on the exam. Like, they're not going to ask you mechanism questions. Mechanisms are only helpful to help you understand the concept.
Okay, thank you.
You're welcome.
Another thing I had a little bit of trouble with, I don't know if you have any tips for me. What can I do to learn how to open up epoxides? I have trouble following with, and I have trouble knowing how it's going to open and where the carbons go on an open chain. I don't know why.
Yeah, that's okay. So basically, first you have to look at whether it's an acid or a base. So in an acid, we know that the order is 3-1-2. And what that essentially translates to is you're going to look at the two sides of the epoxide. So what I'm highlighting, right? And this side in green has 1, 2, 3 carbons attached to it. So it's tertiary, versus this side in pink has 1 carbon attached to it. So it is primary, right? And since we have an acid catalyst right here, what that essentially means is that it prefers the order 3-1-2. And so tertiary would win. And what that means is the nucleophile will attack the tertiary side and it will open the other way.
I think another good piece of advice is to always remember when you're opening up an epoxide, you're going to be always breaking a carbon to oxygen bond. Because I know that used to confuse a lot of people because they would want to cleave it the other way, but you want to make sure that you're cleaving between the carbon and the oxygen, not the carbon to carbon bond.
Okay, so okay, gotcha. Always gonna cleave that carbon to oxygen.
Yeah.
The carbon attacking though, right? Yeah.
It depends if you're doing an acid or a base. So in the acid, we clearly cleave the tertiary side. So we broke that carbon to oxygen bond.
Yeah. Basically, the only time we're ever going to break a carbon-carbon bond is in chapter 19. So until then, pretend it's not possible to do so.
Quick question. I don't
Always the carbon to.
Sorry, Travis, I heard you first, so you can, and I know you unmuted a couple times, so what's up?
Nah, never mind. Katrina already answered.
Oh, okay. Isn't she the best?
No, oh no. I was saying like, sorry. Is this gonna be uploaded on YouTube?
Yes, it will.
All right, thanks.
You're welcome.
So somebody's saying that isn't the CH3OH an acid on its own? Because they're asking about the H+. So do you want to explain that?
Yeah, so... All right, well, there's 2 reasons. One, because Dr. West will just put it in here sometimes. He will literally just put something that you have to say is the nucleophile, and then H+ or H-, and he expects you to just know H+ means acid catalyst, and H minus means base catalyst. But yes, you're totally right. I could have just put nothing down here. And since this is an acid, it will do the same order. And since this one, or the other one that I had in the handout, I don't have it on here, had a base present, then it doesn't have to specify that there's a base in the catalyst. I just like to put that for you guys as some like extra reassurance as we're doing these for the first couple times. That sounded weird. Please let me know if that makes sense or if you're still confused.
So if the H plus is the only thing present, that's what you're going to be adding as the nucleophile as well?
So, no.
Or will he like have a specific nucleophile?
He'll have a specific nucleophile, and that's a good logical way of thinking. But the thing is, H plus wouldn't itself act like a nucleophile because it has a plus charge. So yeah, that wouldn't really make sense, but I understand the idea. So if it was like H minus, that would work, but he doesn't really do that ever, if that makes sense.
Okay, so there will always be a nucleophile and then like under something to signify an acid or a base, correct?
Well, he could also just do it like where, pretend this is not here. He could give you this, and all that means is that you have an acid because CH3OH is an acid, and so you know it would proceed as an acid catalyzed. But 99.9% of the time, he will ask it to you like this. Was that still the case, Katrina, last semester when it was online, or do you not remember?
Sorry, say that again. I was replying back to things in the chat.
Oh, okay, sorry. I don't remember if you took this exam online or not, but when it's been in person, he always puts H plus or H minus on the bottom. So do you know if he did that?
Even when we were in person versus online, even for like the next exam, he usually indicated that. If it's on the practice problems, guys, I wouldn't worry too much about it because his exams are like his practice problems. So it will always, there's always going to be some indicator whether you're dealing with an acid or a base. So don't worry too much about that. As long as you can see whether it's an acid or a base based on like an H plus or an H negative, you guys will be fine.
Yeah. There's one example that he does in class. I don't know if he has it in the online lectures, but it's a weird one where he says that instead of acid or base, you think about stereochemistry. But last time I SI'd, everyone got super confused, and he was like, okay, I'll just remove it from the exam. Don't worry about it. So that's why we're covering it like this only, because I don't want to give you anything that might confuse you. That won't be relevant. Okay, so you guys can continue asking questions, but we're going to go back to this one. So it will attack the tertiary side, open up the other way. So essentially what that means is this ring is not going to change because, again, carbon-carbon bonds. We know that this carbon right here, has one carbon attached to it. So, bam. And we know that coming off of this primary carbon is, again, this O, right? And that will remain wedged because we didn't do anything to it. So it remains wedged and it becomes an OH. Our OCH3, however, has to do a backside attack here. So it will flip the stereochemistry. So it will look like so. Oh. It seems that my screen is frozen. Is it frozen for you guys?
It's not frozen for me. It might just be an internet error on their side.
Okay.
So
then I'll just keep going, and then you guys can let me know if there's like an issue. So the opposite of that is going to be base catalyzed. Since we're not going to do both, I'll just give you chemistry for this one, so you guys have like a good example of everything. So if this one had wedge and we had a base catalyst, we would choose the order 1, 2, 3. And we already knew that this was primary, this was tertiary. So now the nucleophile will attack the primary side. We break this bond and we open that away.
Rosemary, I hate to disturb you, but somebody was asking about if both enantiomers will be formed for that example, the previous one. And I know technically he does say in lecture that you'll form both, but like you'll form one and more than the other. I just don't remember if on his exams he has it as like a mix of both.
Yeah, so essentially in class he always gives you like this disclaimer where in reality you form a bunch of different products. So yes, you will form both enantiomers, but if he asks you this on the exam, you want to put this answer because that is the primary product. So it's the major product.
I'm sorry, I just have a question now for the. Now the oxygen will now be on the tertiary carbon, correct? Because it's opening up that way.
Exactly. Yep.
Well,
Okay, so all right.
well, my question was too. Is I was saying, wouldn't it be a racemic mixture of both enantiomers because it could approach from either side technically? Because it's just a single bond, so there's free rotation, so it could flip over and approach from the top side.
I mean, it could. You're right, but that's like too. He would mark you wrong for that logic. Is what I'm trying to say.
Even though in reality it would probably be a 50-50 mixture.
Probably, yeah. So in reality, it depends on what base you use, what acid you use, like what temperature you're at, all those things. But as far as the exam goes, the way he draws it is the way he wants you to proceed. So if it's written like this, you're to assume that there's going to be no changes to like rotations and everything. So really good question, but a little bit beyond the scope of the class.
I have a quick question.
Yes, shoot.
If we just walk it back for a second and we're talking about that hydrogen, are we going to be asked for like cleaving the epoxide with the acid and water?
Wait.
Like okay, so we have the epoxide.
Yeah.
And then it's in that HBr, like it's reacting with HBr. Will he test us on if the HBr is going to be in water? That's all I'm asking. Because then we would have a solvent effect, correct?
He won't ask you anything like that.
Okay, cool. Just making sure.
Yeah. For a second, I was like not sure what you were asking, but yeah. Okay.
The cost is kicking in.
group, the tertiary one, be like a 40%.
Yes. Okay.
Yeah, so, yeah.
I'm sorry. I heard like
The
three things.
question is just asking the sterically hindered epoxide with a cyclic group, the tertiary one, be like a 40% contribution.
Yeah.
Yeah,
We can say that.
we can say that.
Yeah.
Okay, you're echoing now.
Oh my god.
Oh my god!
Oh my god. This is the worst thing.
Okay, I think you're good now. Sorry, guys. It's just that whenever we connect something else to it, we get feedback from our two different devices. So, very sorry. Rosemary, do you want me to do or are you good now?
Okay, I think I'm good, but my laptop is not on. So can you guys like hear and see me?
We can see you and we can hear you.
You know what?
Okay.
This is fine.
Hold on.
This is fine. We're just gonna go on. Everything is okay. So I still can't see the chat. That still remains the same, but I'm just gonna keep talking because I don't want to waste your guys' time. Anyways, let's get to it. So we attacked the primary side.
Question that was
Sorry, yes, what?
The question that was asked was about sterically hindered epoxide with a cyclic group, the tertiary one, be like a 40% contribution.
Yeah?
I don't think they need to worry about that for the exam because he's not really one to ask for like the smaller product versus the bigger product.
Yeah, he won't do that. That's a good idea, and I think you would be correct, but he won't ask you anything like that. Okay. So, we will have the OH keep the stereochemistry on the tertiary side, and the new group will be the opposite, so flip stereochemistry, and it will be like so. So yeah, I just got really flustered, so I don't even know how to explain this last one or like what I already said. But essentially, since it was in a base catalyst, the order is 1, 2, 3. So you attack the primary side and open towards the tertiary side. The side that gets attacked flips stereochemistry, and the side that did not do anything kind of just stays the same.
I have a question.
Yes.
So if you're given a molecule that has a benzyl in it, but it's in a basic solution, would you like? Let's say there is like 2 carbons after the bend of the benzyl, and then there is a tertiary position on the other side. Which one would you pick? Do you count it as benzylic, or do you just say like right next to it there's a secondary? Like what I'm trying to say is that does allylic and benzylic positions matter if it's basic, or do you not worry about that?
You know, yeah, I was
And
going to
only
explain it, but honestly, just don't worry about it. It's not going to pop up for this stuff.
Okay.
Okay, so we're going to speed through Redox stuff because it's already been like an hour, and that was a whole mess. And you guys don't need to know oxidation for this exam, according to Dr. West, so I'm only going to give you starting material and final products for this page. So, one thing I want you guys to remember is anything with O4 or more is going to be strong, and PCC is going to be weak. So if we have primary with a strong, and I'm using S for strong, we're going to make an aldehyde, or excuse me, we're going to make a carboxylic acid as our final product. If we have a primary with a weak, we are going to make an aldehyde. And for the secondary, it doesn't matter whether we have strong or weak. Either way, we will form a ketone. And the reason for this is because we have 2 carbons. We can't get rid of carbons, so we have to end up with 2 carbons at the end. And literally, if you know that, that's all you need to know for oxidation. For reduction, we're essentially just doing the flip-flop of oxidation. So for weak reducing agents, we have NABH4. For strong, we have LiAlH4. And so the weak reducing agents can only reduce aldehydes and ketones. And the LiAlH4 reagent can reduce everything. The thing with DIBA is that it can only reduce esters and carboxylic acids, but it stops at the aldehyde. And before I start showing you the answers, I just would like you to note that for the second one, I had accidentally drawn 2 ketones instead of an aldehyde and a ketone, so I added a hydrogen, so don't get confused. So if we did a ketone, we could use either one. It doesn't matter, so I'll write either. And we will get, or you know what, I won't write either. You know what, I will. That's fine. We're going to add 1 hydrogen, and this becomes an OH. So it is a secondary OH. With the aldehyde, we can use either again, and we will add a hydrogen, and we get OH, and this time it's a primary alcohol. For esters and carboxylic acids, we have to use LiAlH4. And the cool thing is, even though they have different leaving groups, all this means is that they will attach 2 hydrogens. So you reduce twice. So you end up with a primary OH for both.
I'm sorry. Could you draw the arrows, please, for this one?
So
Thank you.
I have the arrows. No, okay. So don't say thank you yet. I have the video on YouTube, and I have the what is it called? Canvas thing. The SI sessions recorded. So I'm not going to draw the arrows for the review, only because I promise you won't have to draw them out on the exam. And we have a bunch of stuff to go over, so I really don't want to like spend way too much time on stuff you guys don't need. I apologize, but I think that's going to be better in the long run for you guys. Okay, so the last thing I want to say about reduction that's important is that the reducing agents are NABH4 and LiAlH4, but the reducing species is H- always. And someone wanted to screenshot the page, so I'm just going to leave it like this for a second, and then we will move on.
I'm sorry, what do you mean by reducing species?
So that's just another name, essentially. So the reducing species is just the nucleophile in a reduction reaction. So the reagent is this whole thing. but the thing that's actually doing the reducing is H-. And that doesn't look like a minus, so let me make that more clear for you guys. Does that make a little bit
Oh,
more
I thought
sense?
that was an OH.
Yeah, no,
Yes.
that was just completely my bad. I'm sorry. There you go. I hope that makes a little bit more sense. So we're going to start chapter 13 now, unless, Katrina, were there any questions?
Sorry, I have so much crap on my table right now. I'm just answering somebody's about the ester being broken into 2 primary alcohols. I'm just going to do this unmuted. So when we are doing the reduction of an ester, you're not worrying about the second product of the part that broke off. You are only worrying about the part of the carbonyl group that we're dealing with. He won't ask you for what the 2 products are. You're just going to end up with whatever happens for that carbonyl. So no, you won't have 2 primary alcohols as the answer. You will just have 1 primary alcohol.
Exactly.
I hope that makes sense.
I have a quick question. So to kind of shorthand that these problems, we will always get these exact same products if we have like a ketone or aldehyde or whatever. We don't have to actually draw out the mechanism or anything like that.
Exactly. So, of course, I'm not going to say just memorize starting material, final product, but no matter what kind of ketone you have, no matter what kind of aldehyde you have, if you react it with the reagents that we listed, you are going to get a primary alcohol or a secondary alcohol. Anytime you oxidize a secondary alcohol, you have to get a ketone, you know? So knowing those kind of trends is super helpful.
Thank you.
You're welcome. Okay. So conjugation is the, in my opinion, easiest part of this chapter, because there's not really much to do. You kind of just have to look at it. And so first thing is first, a diene is a compound that has 2 double bonds. Diene, 2 double bonds. And conjugation is more specifically when you have 1 double bond, 1 single bond, and then another double bond. So 2 double bonds that are 1 single bond apart. So this is conjugated. We also have a condition where we have 2 double bonds, but they're super far away from each other. So they're more than 1 single bond apart. And this is called isolated. And I laughed because I saw like a notification pop up that said I'm dying, and same. So isolated is when they're more than 1 single bond apart, and cumulated is when multiple double bonds are on the same carbon. I spelled that wrong. So just to recap, conjugated, 2 double bonds that are 1 single bond apart, isolated, more than 1 single bond apart, cumulated on the same carbon. And
Rosemary, do you mind just naming the first bond really quick? Like giving the name of it? Like how you would name a diene? That's it.
Oh, yes.
Isn't it 1,3-butadiene?
Yes, so it is 1,3-butadiene, and that's important because he will often just write 1,3-butadiene instead of drawing it out. So that one you should know by name. If it's more complicated than that, he'll show it to you. He won't just give you a random name. And the last thing you need to know is order of stability goes this way. Least stable is cumulated. Most stable is conjugated. Now, as far as configuration and conformation go, essentially all you need to know is configuration is used when we're talking about a single bond sandwich with a double bond in the middle. And we're going to name it either E or Z. So the way I remember what's E versus Z is when they are on the same side, this is Z. When they are opposites, they've had enough of each other, so that's E. I was going to write something and I
Is
forgot.
E always more stable?
What was that?
Is E always more stable than C?
So I'm never going to say 100% of the time because chemistry is weird, but 95% of the time, yes, it's always more stable. So I will actually write that.
Which one is?
E. And the reason E is more stable is because it's trans, so they're going away from one another, so they have less steric hindrance. And the last thing I want you guys to know is that since we have a double bond in the middle, you can't flip between these two. So you cannot interconvert between the E and Z. Conformation is when you have a double bond sandwich with a single bond in the middle. And so we're actually going to cut this double bond, we're going to cut these single bonds in half. And if the double bonds are pointing away from one another, this is S trans. And then if the double bond is, if the double bonds are pointing toward each other on the same side, we are going to call that S cis. And just like in the other example, S trans is the most stable. And that is because of sterics again. However, now we can rotate on this single bond because unlike the double bond, it doesn't have this rigidity to it. So we can interconvert between cis and trans. So if we look at these dienes and we try to rank them in order of most to least stable, one thing we have to take note of is the order of stability for double bonds. So when we have a primary substituted double bond, or mono-substituted double bond, that means that there is only one substituent, so it looks like so. The rest would be hydrogens. And then we have a di-substituted double bond, which can either look like this or like this. And then a tri-substituted double bond. And then a fully substituted double bond. The more substituted it is, the more stable it is. So if we look here, we see that it's di-substituted, di-substituted, mono-substituted, 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 mono-substituted. So the first thing we're going to see is this answer choice has two mono-substituted double bonds. So it is immediately the least stable. So 4 is in last place. It's the least stable. And then we have options 2 and 3, which each have one mono-substituted double bond. So let's go ahead and find out what the configuration is here. So our group is pointing.
And I was going to ask you about that. For the, oh, sorry.
Yeah, no, go ahead.
For the I was going to ask, for the configuration, are we looking at the groups or are we looking at the hydrogens?
The groups.
The groups, okay, gotcha.
Yeah, because you're always going to want to pick the group with the highest priority and go from there. So since these two priority groups are pointing opposite one another, this is E. If you look at number 3, though, they're both pointing up. So this one is Z. So the Z configuration will be less stable. So we know that 3 is next. More stable than 3 is 2. So now we're stuck between 1 and 5. So for 1 and 5, we're going to do the configuration and conformation. So configuration first, we split it in half, opposite, opposite. So this will be E, and this will be E. And then if we look at this single bond right here, the conformation, we can split a line, and we see that one double bond is pointing down, one double bond is pointing up. So this is S trans. Okay, this looks good so far. If we look at 5, and we cut the double bonds first, we have one pointing up, up. Uh-oh, that means it has to be Z. On the other side, it's pointing one down, one up. So that means it is E. And then this single bond in the middle, if we cut that in half, we see the double bonds are pointing away from one another. So this is, again, S trans. So if we have EE S trans and EZ S trans, we know that the one that has the most E configurations will be the most stable. So we can say that the most stable molecule here is 1, and then we have 5, and then 2, and then 3, and the least stable would be number 4. Someone said we're losing her in the chat, and I'm scared. Does that mean it's not working? Okay. Whew.
False alarm. You're good.
Okay, great. For a second, I was about to start crying. I was like, not again. All right, so I took up way too much time. I apologize for all the technical issues, but do you want to take it from here, Katrina? Or do you want me to do UV spec? I forgot.
I guess that's me.
Okay.
Okay.
So let me...
So, I'm going to... Oh, I took off. I kicked you off.
That's okay.
Okay. All right, guys. So now we are going to go into chapter 13. I'm going to low-key speed run this just because we're running out of time. I'm only going to cover what you guys need to know for the exam, okay? So it's about anything else that is out of this zone, because chapter 13 can be a lot if you go to depth. Okay, so UV spectroscopy, the main things you need to know about it is what happens if you have something that is highly conjugated. So the more conjugated your molecule, the longer your wavelength is going to be, and the lower your energy and frequency will be. So please, please, please know that your conjugation and your wavelength move together, and then your energy and frequency move together. So just know that. That's all you really need to know for UV spectroscopy. And on the off chance that he asks you about the Beer-Lambert law, the only thing he would possibly ask you about is what each one stands for. So because of that, I'm just going to go ahead. This is what it looks like. I think this was supposed to be an L. So A basically stands for absorbance. This guy here stands for molar absorptivity. C stands for concentration. And L stands for path length. Sorry guys. I don't know why, but my iPad always has this issue. Okay. That is all you need to know about UV spectroscopy. The more conjugated your molecule, the higher the wavelength and the lower the energy. If he ever asks you a beer log question, he's never going to ask you to calculate anything. Do not need to know calculations.
So for less conjugated, which could be isolated, it would be shorter wavelength and higher energy or higher frequency?
Yes, exactly. So if you are choosing, let's go up here to these problems. This one will have a high conjugation because it is conjugated, and then it will have a high wavelength and a low energy and frequency. I'm sorry, my handwriting's not as neat as Rosemary's. So if you had to choose between these two molecules on which one will have the higher wavelength, it's going to be 1. If he was asking you for which one has the higher energy, it would be 2 because it's less conjugated. Does that help? Everybody good?
Absolutely.
All right, cool. Just making sure. Why couldn't it be 4? Andrew, I wasn't just referring to 4. I was just looking at these two molecules right here. I was just comparing those two as a quick, little example. Yeah, don't worry about it. Okay. So, molecular orbital theory. This is going to 100% be on your exam, but it's not going to be as hard as you guys think it is. All right, so 1,3-butadiene, and I promise you guys, these guys right here, the allyl cation, radical, anion, and 1,3-butadiene, almost 95%, this is all he's going to ask you about for molecular orbital theory. So do not worry about other molecules for this. This is all you really need to know. Okay. So the number of, I always like to start with the number of molecular orbitals, okay? So the number of molecular orbitals is how many pi orbitals you have present. So right now, if we just count how many are drawn here, we have 4 molecular orbitals. And then because of that, you need to note that a pi bond will give you 2 electrons. So we have 2 pi bonds, so we will have 4 electrons. I'm not going to write electrons because it's already there. I'm going to skip, Rosemary, by AO, you just mean antibonding orbitals, right?
Just atomic orbitals. So I included it just to be super inclusive, but atomic and molecular orbitals are going to be the same.
Okay, because I assumed it was antibonding, but yeah, okay. Thank you for that. All right, so
wait, I'm sorry. So for the molecular orbitals, we just count every carbon, basically?
You're not Rosemary, would you say for the most part for this exam, technically you are just counting the carbons? I mean, that's not really how it works, but...
Yeah, so that's not actually how it works, but in this case, you can count it like each carbon that has a pi orbital, or a p orbital, excuse me. So as far as this exam goes, yes, it's each carbon. In general, no, that's not the case.
Okay, so we are going to go ahead and go into this one here. All you have to do, the number of molecular orbitals is the number of lines you draw. So as you guys can see, we had 4 molecular orbitals, so we drew 4 lines. And all you have to do is fill in your electrons. Remember from Gen Chem, you always want to start at the lowest orbitals. So we are going to go up 1, down 1, up
Hello,
1,
Katrina?
down 1. Yeah.
I'm sorry to interrupt you. What's AOS? AOS.
She said this one is just atomic orbitals. Don't worry about it. He won't ask about it in the exam. You only need to know molecular orbitals, so don't worry about atomic orbitals. She just added them there, so
Okay.
to be inclusive. Okay. So as you guys can see here, whenever you have an even number of molecular orbitals, the top half will be antibonding and the bottom half will be bonding. Okay? So our HOMO and LUMO. HOMO stands for highest occupied molecular orbital. So even if it had one electron in there, it will still be considered the highest occupied molecular orbital. Our LUMO is going to be the lowest unoccupied molecular orbital, meaning the one with no electrons present. So as you guys can see, that is why pi 3 is our LUMO, and then pi 2 is our HOMO. Okay, so when you excite an electron, all it does is push one electron up into the next one. So in this case, we take one of the ones from our bonding pi 2 orbital, and we push it in to here into the anti-bonding orbital.
So is the trend that it always goes from HOMO to LUMO?
I'm going to say yes. It will always, because your HOMO will always have the electron. So then whatever you had in the highest molecular orbital is going to get pushed up to the LUMO. So yes, E, you are totally right.
Okay, perfect.
But notice, guys, the HOMO and the LUMO state stays the same. So it doesn't matter that I threw an electron in here. The LUMO will still be pi 3. Okay. So another spin that he could give you guys is the allylic cation. The allylic cation will still, this one will have 3 molecular orbitals and 3 atomic orbitals. And then we have 1 pi bond. And that positive charge denotes that we don't have an electron on the N carbon over here. So because we only have 1 pi bond and there's no electron here, we are only going to have 2 electrons for this molecule. Jessica, there's not really a, for right now, okay, yeah. Rosemary answered, okay. So now we're gonna go in and do the same thing. You guys see we drew 3. Rosemary, is this one supposed to be non-bonding?
So yes, what had happened is for some reason last semester Dr. West decided to call that one exclusively non-bonding, and I forgot to change it, but this semester it's back to normal, so it would be non-bonding again.
Okay, so hold on guys, sorry. Little technical thingies. Oop. This is actually non-bonding. Okay. A bit confused of how you got 2 for pi. So do you mean the 2 electrons? So basically we're counting, this is just asking how many pi electrons we have present. And because we only have the 1 double bond here, remember 1 pi bond gives you 2 electrons. So we only have 2 electrons present because this guy here isn't giving us any electrons. It's just a positive charge, denoting that there's no electrons there. You're welcome. Okay, so once again, we're filling in our lowest orbital. And as you guys can see, that ends up being our HOMO. Our non-bonding pi 2 is our LUMO.
Can
So
you explain why
How do
the
we have a
node
non-bonding?
is going through the other orbital in the middle?
So you're talking about this one for the non-bonding?
Yes, like can you explain why the node is going through the middle orbital?
Yes.
Because he was
Okay.
talking about that in lecture, but I never understood what he was saying.
So basically, if you have an odd number of pi orbitals, just know that the middle orbital is going to be your non-bonding orbital. And that is because when you go up a level, the node always needs to split in half. It splits anything in half. So if we looked up here at this one, when we went up a level, the node was able to split right down the center. So that's exactly what it was doing here. It split right down the center. And that is where the non-bonding one comes from. Did that help?
Yeah.
Okay. You don't really need to worry about how the non-bonding is formed for the exam. You just need to know that it exists when we have an odd number of pi orbitals. That's it.
So it would also work for, let's just say, 5. 5 is an odd number, so it
Exactly. So pi 3 is still going to be, our pi 3 would be our non-bonding orbital. Perfect. Okay. So now all we do for our excited one, we take one of the electrons and upgrade it. So as you guys can see here, LUMO and HOMO stay the same. And that's basically it for that one. Okay. So now we're dealing with the allele radical. So note on the allele radical, this guy at the end over here is going to have an electron. It is just a singular. If you didn't have the pi orbitals drawn, this is what your allele radical will look like. And that little speck indicates an electron. Okay. So the number of molecular orbitals that we have present is 3 again. The number of pi electrons this time is going to be 3 electrons because we are getting 2 electrons from this double bond and then this additional electron from our radical. So once again, this is just atomic orbitals. Don't worry too much about it. So I'm going to go and start filling in our molecular orbitals. So as you guys can see, we have 1 lonesome electron in our non-bonding, but because we still have an electron present, that is going to be our HOMO. And then our top one is going to be our LUMO. So we are going to excite that singular electron, and now we have this. It's weird. We are not just counting the electrons participating in the pi bond, we're talking about the molecule itself. Rosemary, is that like a proper way for me to say that?
Yes, so I was just writing it in the chat. Essentially, anything in a p orbital. So since radicals, cations, and anions count as p orbitals, that's why we count them.
Perfect. Thank you. Guys, exam Monday, Wednesday, Friday, and Tuesday, Thursday all have the same exact number of questions and the same time period. He doesn't change anything between you two. Just wanted to let you guys know. Wouldn't HOMO be at the bottom? Remember, HOMO just stands for highest occupied molecular orbital. So even if there was 1 electron present, it is still considered a orbital that is occupied. So our HOMO would actually be our non-bonding. Would a lone pair for the allele fill both bonding and non-bonding? Hold on, there's so many chats coming through. Would a lone pair for the allele fill both? Yes. So that's exactly what's happening in the next one, Andrew. So we have 3 molecular orbitals. This time, our allele anion, when you see that negative sign, know that this negative stands for 2 electrons. So basically, if you wanted to draw this as that, you could draw it with 2 dots like this. And then we're getting 2 electrons from here as well, because that is our pi bond. So we will have a total of 4 electrons in this molecule. So we're going to go ahead and draw in our electrons. And as you guys can see, our non-bonding orbital now has 2 electrons versus the one up here that only had 1. So we're going to do the same thing. We're going to excite one of the electrons. And now this is what we end up with in the excited state. Once again, note HOMO and LUMO do not change regardless of whether or not it has an electron in it. So guys, please, please, please just know these, know how many electrons are in each pi orbital. Know an easy Dr. West question that he could give you is, in the allele cation, how many electrons are present in the anti-bonding molecular orbital? And the answer would be 0 electrons. Read the question carefully because he can spin that in about 5 different ways. Okay. I am definitely running out of time, so the Kahoot will probably run over our time. So yeah, just giving you guys an FYI right now. So now we are on to 1.2 and 1.4 addition. So basically this is we're going to identify which one is the nucleophile, electrophile, 1, 2, 1, 4, thermo, and kinetic. So our nucleophile is going to be the one doing the attacking. So the one that's doing our attacking in this situation is A, because it is our double bond that is attacking, as you guys can see in the reaction mechanism. Okay, and then our electrophile is the one being attacked, which in this case scenario is B, because the HBr, the hydrogen of the HBr is being attacked. The 1,2 product is simply this. The hydrogen got bonded to the first carbon, and the Br got bonded to the second carbon, and that is why it's called a 1,2 product. If we look at D, this hydrogen got bonded to carbon 1, here's carbon 2, 3, and 4. That is the only difference between those two. As you guys can see, C is going to be less stable because we kind of just threw them into the corner together. And this thing here, basically our cation isn't going to be as stable when we're doing resonance. So our 1,2 product is going to be C, our 1,4 is going to be D. Thermodynamic product is our most stable product. Remember that. Thermodynamic is the most stable product. So in this case, that will be D. And then which of these is the kinetic product? That is going to be C, because that is our 1,2 product and is less stable, because if you look at our double bond, it is not as substituted as the product in D. Is it always the least substituted? Rosemary, do you want to answer that one in the chat? It's just about 1,2 addition and if it's always the least substituted.
Yes. Okay. So essentially, yes. And the reason, well, as far as this class goes, because, you know, chemistry is weird, but in this class, the least substituted one is the most reactive. So it's the least stable. So that's why it's more likely to react.
Yeah. Okay.
Welcome.
Okay. So he will likely give you guys a graph like this, and he'll ask you what is the fate of the intermediate of this reaction mechanism. So all you have to do is know this is our intermediate right here. I like to draw a line because I like to see where the intermediate is. So I go ahead and draw that line. And then I compare two things. This represents the amount of activation energy it's going to take to form that product. This one here is how much it's going to take to form this product. A kinetic product will have a lower activation energy, meaning a smaller hill. Let me actually put this in the proper colors before I mess everybody up. Lower activation energy. And it will be the main product in a low temperature. Okay. Our thermodynamic product will be our more stable product 1. It's going to have a higher activation energy. It will also be our main product at high temperature. So what I mean by more stable is this chart here is going in the flow of potential energy. So if you look here at B, this one is going to be a less stable end product. Oh, less stable, and this one here will be more stable because it has a lower potential energy at the end. So shouldn't B be lower than A in the graph since B is more stable? So this graph does not have to do with that situation that you're discussing. I was just comparing the kinetic versus the thermodynamic product, and that's where that chart came from. Thermo can have, the thermo product, because it's more stable, will have a low PE. I might be confusing people at this point in time. Okay, so let me just zoom in on the chart, and we're not going to pay attention. Go ahead.
Can I just say something real quick? Okay, so basically how I explain this, because people always get super confused about kinetic versus thermodynamic on the reaction diagram.
Mm-hmm.
So I am going to say this super loud and super close to the camera. Never talk about higher energy. So we're actually going to go in terms of only lower energy. So kinetic product is going to have lower activation energy, while the thermodynamic product is going to have lower potential energy. In some cases, we can work it out that one is higher than the other, but in general, we're never ever going to use in terms of higher. And the reason is because the thermodynamic product and the kinetic product can be the same. So in that
I'm
case,
going to erase this.
Okay. Sorry. The only reason I say that is because I explained it a little bit like that in my first semester, and it confused people a lot. So the lowest kinetic energy, the lowest potential energy means that it has the lowest product. So in this case, A, like Katrina said, is lower on the diagram, which means that it has less energy. It's more stable, right? And so we know that that one has to be the kinetic product. B, on the other hand, if we use the logic that we were doing before, then that one would have to be the thermodynamic. Excuse me. I missed myself. So sorry, guys. So the lowest potential energy, like we said, is the thermodynamic product. I misspoke. So A would be the thermodynamic. And then if you use the other logic, you would have to say, oh, well then B has the higher potential energy, so that one has to be kinetic, right? But that's not the case, because we're only talking about lower energy. So lower activation energy is always the kinetic product. And as Katrina just wrote in green, the one with the lowest activation energy is still A. So in this case, product A is both the kinetic and the thermodynamic product. I know I stuttered a little bit, but I hope that makes a little bit of sense. And yeah, essentially B is nothing important. It's just the other one. Sorry to interrupt. I hope that was helpful.
No, I hope that explained it better than what I could do. So yeah, basically that's all you really need to know about this. Be able to understand how to read the graph like we just did. So you want to look at activation energy, and then you want to look at the energy of just the diagram in general. So the two things that you're looking at is this hill, and then you're looking at A and B. That's it. So in this case scenario, go ahead.
So A is the lower activation energy, N is the lowest potential energy also at the same time, correct?
Yes, exactly. So yes, Travis, you are right. The more stable one is forming more quickly in this case scenario because of this activation energy thing. Okay, so something I want you guys to know though, if you see these two words, equilibrium or reversible, please note that our thermo / more stable product will be favored. Okay? Please, if you see this and you see equilibrium or reversible, just know our thermodynamic product will be favored over our kinetic. Okay. So that brings us into the last portion of what we are doing before we do the Kahoot, and that is Diels-Alder. We did not get to do too much of this in SI, but no big deal. So some things to note about the Diels-Alder reaction. It is concerted, and all that means is that everything takes place in one huge messy step. Reversible means that we can do retrosynthesis of a Diels-Alder reaction mechanism. Thermal means it needs to take place in heat, which makes sense because remember we were dealing with thermodynamic before, and that needs a high temperature. And then basically it's a cycloaddition, so we are just making a cyclic group right here. So the way this reaction mechanism takes place is simply this. Our double bond here is going to attack this double bond, push this one like this, and then that one is going to attack it as well. So basically, if you see all these arrows, they're all attacking each other. So the way it looks, Rosemary might be able to explain this better, but the way it looks, know that our single bond is going to form where our double bonds used to be. And then we just add on these lines here. So if it makes more sense to you guys to think of it this way, these dashed lines is really where the bond moves. Okay? If you need to draw on those dashed lines, draw on those dashed lines, and then just know that's where that double bond moves to. And that is how we form this compound here. So some things to note about your diene versus your dienophile. Our diene is going to be our nucleophile. It's going to be conjugated, and it needs to be in the S-cis configuration. If it's not in the S-cis configuration, we won't be able to use it unless it has that rotation around a single bond. It is also going to be an electron donating group, meaning that it is going to want to give electrons away. So our dienophile on the opposite side is going to be an electrophile. It will be an alkene, meaning we just have the one double bond, or it could be an alkyne, which is simply a triple bond. It's going to keep its configuration. So let's say we had groups on here. One was wedged, and the other one was dashed. It's going to keep that same configuration when it adds on. So we would still have a wedged one over here and a dashed one over here. And it is going to be an electron withdrawing group, meaning it's going to want to steal those electrons because it is very greedy.
I'm sorry, can you explain the configuration again? Yeah. So I just drew these on. So basically, if we have groups like this on our atom, on our alkene or alkyne, basically, it's just going to stay the same when we add it on. Nothing changes about this. It does not get inverted. The configuration just stays exactly the same. So if we had a CH3 group here and a CH3 group here, at the end, we will still have the same exact groups and nothing changed. So for the diene, the configuration changes?
The diene, it doesn't really change because it doesn't have any groups on it. You will rarely see a diene that's going to have a group on it. Your dienophile will usually be the one that has groups on it, like a carbonyl or a, I don't know what other groups you could see on there. Usually it's just a carbonyl.
Can I be really annoying and interrupt for a second?
Please.
Okay, so for the configuration and confirmation thing, Katrina was right. The only other thing I want to add is you're looking at two different concepts, right? Because the dienophile has its configuration versus the diene has the conformation. So we're going to ignore configuration in the case of the diene. And the other thing I wanted to say is, yes, okay, so as far as electron donating and withdrawing groups go, yes, you were right in saying that the diene would donate the electrons and then the dienophile would withdraw electrons. But also I want you guys to know that there are actually like substituents and any kind of stuff that you can add to the diene and to the dienophile, which will either add electrons or withdraw them. So something like an OH, since it has a lone pair of electrons, it will donate those electrons to the diene, and that'll make it react much faster, versus something like a carboxylic acid that is going to withdraw electrons, so that would be better for the dienophile.
Okay, so will the product of the diene will it always be as cis?
The product of the diene, okay. I'm not 100% sure what you're asking, but again, at this point, we would, like in the second one, in the product, you wouldn't have conformation anymore because you only have one double bond. But in order to react, you have to be an S-cis conformation.
All right, they said okay in the chat, so I think it made sense. Okay, so basically I just put a bunch of electron donating groups versus electron withdrawing groups on here. As you guys can see, electron donating groups will either have lone pairs or negative charges. That's typically how we deal with it. They're usually the R groups because those are the ones that are going to be electron donating. And then the electron withdrawing groups are usually going to have a positive charge. These includes any carbonyls like our aldehydes, ketones, carboxylic acids, esters, you name it. And then it can also be halogens, which are like Br, Cl, fluorine, all of those guys. Rosemary, anything you want to add to this one? Okay.
Oh, sorry, I didn't realize I was unmuted.
It's okay. I was just wondering if you had anything to add. So that is basically it for this. I do have some questions in the Kahoot that will give you guys some practice on the Diels-Alder. So if you guys are good, I will leave this page up for a second so you guys can screenshot it if you want. And then from here, if you guys are cool with it, we'll start up and do the Kahoot.
Wait, I kind of zoned out. Did you guys mention about the EXO and the other one, or is that not really important for the test?
So, basically, since we went overtime, we kind of decided to keep the Diels-Alder short and sweet, because I have like a 30-minute video about just Diels-Alder that will be up, probably posted today, and we'll finish covering it tomorrow in SI. So this is like the basic, most important stuff that you guys need, and all the little bits and pieces and details will be posted like as a recording so that you guys can see later. But just endo is like 99% of the time most preferred.
And I don't think I remember seeing a question like that on my exam, to be perfectly honest, and that was in spring. So I wouldn't worry a crazy lot about it, but if he does throw one at you, just know that, like, the way I like to think about it is that the endo is like, I don't really know. How do I phrase this properly? Rosemary, do you have like an easy way to phrase it?
Yeah, so the way I think of it is like, exo is like an exoskeleton, it's going outward, endo is going inward. So the ones that are pointing in towards the double bond are endo. The ones that are pointing out are exo products.
So, okay, so basically what Rosemary meant by that, I'm sorry guys, I just kind of, it's usually going to be on a bridgehead like this. And basically if the group is here versus the group is on something, oh my God, I can't draw a bridgehead for the life of me. Okay. This is a horrible bridge versus that. Is that what you meant, Rosemary?
Yes, exactly. So the one that's pointing down is the endo because it's pointing in. The one that's pointing up is pointing away, so that one is exo.
Okay.
I have
So
a quick
if-
question.
Yeah, go ahead.
So if our diene isn't in that S-cis configuration, would we just say that the Diels-Alder reaction doesn't go? Or can we just twist it like the S-trans into an S-cis configuration and move forward?
That's
Okay,
an awesome
so
question. Oh, sorry. Go ahead.
All right, so basically, if you have something that's in a cyclic compound like this, if this thing was not in an S-cis configuration, you cannot rotate it because it is in a cyclic compound. But if you had something that was just like this, like this, you can rotate around the single bond.
Awesome.
So you can make it into S-cis.
The only time you couldn't do that, Katrina's like 100% correct. Sometimes he will throw this at you though. If you have a tert-butyl group on the two sides of the single bond, if that makes sense.
Okay, so just beware of the chicken foot.
Exactly.
Yes,
so if you
beware
have
of the chicken foot.
it won't work.
Thank you.
So Jessica, to answer your question, basically this would be your diene and this would be your dienophile. So the cyclopentene is still it's going to be your diene, so it's going to be your nucleophile attacking that dienophile. So yes, you can still use it because it is in the S-cis conformation because this is S-cis. Okay. So if anybody else has any questions, I'll keep the chat up, but I'm also going to just start the Kahoot now because we are kind of out of time. But it doesn't matter. Exam reviews run over all the time, like Rosemary said. So let me pull up this Kahoot.
There was once like a 5-hour exam review, so.
Okay. So I just have one more question. So basically, you would say that everything that we covered here today would pretty much be the most important things that we should know, right? Besides,
yeah.
Okay.
Okay. This is what I want. Unfortunately, we will not have any Kahoot music because I can't do music on my iPad or else we're going to get horrible feedback.
I can do music. That was mostly a joke.
Jessica, you don't need to know protecting groups for the most part. The only way you'd have a protecting group on the exam is if it's in a multi-step synthesis reaction mechanism. But that is it. The other one, what other one are you referring to? Wow, this is a lot more people than I'm used to having in a Kahoot game. I'm like seeing all these names and I'm like, wow.
Also,
go
I
ahead.
love the spooky names that some people have.
Know that the protecting group is just going to replace the OH. So if you had PBr3 and then you had a alcohol, the BR will go where the OH is. And there might be a problem in this Kahoot that goes over a multi-step like that, but if not, if you guys want to stay after, I can show you guys one of those problems and what happens. It is all up to you guys. This Kahoot is about 30 minutes long, but it also can be a lot shorter if you guys all answer sooner than the time period. I will let you guys know this much. I love how somebody's named Dr. West, by the way. Yeah, Grignard, basically. Usually you'll see the protecting group end up turning into a Grignard because you'll have PBr3. So the alcohol reacting with a PBr3 will create the alkene with a BR, and then all of a sudden it'll turn into a Grignard. We'll go over that problem, don't worry. So I made these names a little... I made the questions all different, like, time periods, like how long you have to answer it. And that's just because I want you guys to be able to get used to the timing of how fast you should be answering the questions. I'm a little confused on what the explanation. I'll show you guys for that one about the exo versus the endo on the top. We'll go over that. Is all of 11 and 12. 11 and 12 is on the exam, but oxidation, protecting. So basically, ethers onwards will be on the exam for chapter 11. And then just know all of 12 will be on the exam. Oxidation, maybe not so much, but like, yeah. Okay. So I'm going to go ahead and get started. We have 47 people in. I'm going to assume that's all that wants to join. So I'm going to start the game.
I love Turtle Mom, Dr. West, Dr. Saint Germain, dead. You guys are... I love it. Okay.
Do you guys want me to play some background music? I don't know what songs you guys would want. You can just play some, like...
Can I play Halloween music?
Yes, do it, Rosemary, do it.
I have a playlist for this.
All right. This was more of a conceptual one. Yes, guys, a peroxy acid and a halohydrin can be used to prepare an epoxide. This is simply just a conceptual one. He probably won't ask you a question like this, but this is just to make sure you guys are paying attention and know how to prepare an epoxide. Okay, onwards. Oh, that makes me so happy. Look, I'm dying here is winning. Okay.
Thicky is my new fave.
Okay. Rosemary, is your music playing?
Yes.
We can't hear it. Oh, there we go.
Okay.
Can you play something more motivating? I'm sorry. I can't listen to it. It sounds like a play. I'm sorry.
Rip. Wait, you've never heard This Is Halloween?
I don't know what that was, but I mean, maybe some Meek Mill.
Well, first of all, you're canceled. Second of all, I'm kidding totally. Third of all, sure.
Halloween is canceled.
All right, I'm going to skip because I feel like everybody answered. This one will be equal amounts of 3 and 4, and the reason for that is because notice how it's just saying that you have an aqueous base that's converting it. And as you guys can see, when we have that epoxide there, both sides are going to be the same. I'll explain this one in more detail later, but basically both sides are the same, so it doesn't matter which side you attack. John, you just kind of assume that the the CH3 groups. So those epoxidation.
I think those are supposed to be hydrogens.
Yeah, those are supposed to be hydrogens. I don't know why on exams he doesn't include the hydrogens, but that's basically just saying they're hydrogens. Okay, so next. Andrew has taken the lead. Daisy is our highest climber.
You didn't want Halloween music. What do you want from me? I have 2 moods, guys. There's the Hot Girl Summer playlist, and then there's Disney and Halloween.
I'm sorry, I had to mute myself. That was too funny.
I'm gonna stop. That's embarrassing.
All right, I hope you guys are getting this one fast. All right, right, so it's asking which one of these ethers is least likely to undergo significant cleavage by hot aqueous H2SO4. We are looking for the one that is least likely to undergo this cleavage, and that is going to be our primary ones, which is 1, because we have 2 CH3s on the sides right there. Everything else will cleave faster than that because we are doing hot aqueous H2SO4. So yeah, okay. Next. Travis has hit a streak.
So, someone in the chat asked, I thought secondary were the least reactive, and, sorry, someone else said something and it distracted me. So basically, one second.
I'm sorry, Rosemary needs to pull herself together for a minute. Okay, guys.
Okay, I'm sorry, I had to stop the music. Okay, so secondary ethers are, less likely to be attacked, right? But when we're talking about just which of the following are like least stable or least likely to react, we just want to know which one is going to make the worst intermediate or the worst carbocation, if that makes sense. So a primary carbon, if you cleave it, would be a really, really bad carbocation, versus the secondary one would be a slightly better carbocation. But if we were doing an actual reaction and we were like attacking one side, then the order you're talking about would still stand. I know it's a little bit weird, but does that make sense?
They said okay, so I'm gonna assume they agree. Okay, so it says epoxides are able to be cleaved in acid and base. Yes, this is true, guys. Remember, our epoxides can be cleaved in acid or base. Our ethers are the ones that cannot be. I'm sorry, Jessica's killing me right now. Ethers are the ones that can only be cleaved in acid. Okay, onwards. Jessica, stop distracting me.
Also,
Yes, Andrew, with that streak.
Yes. And also, I'm sorry that we're being so goofy today, but like this has been the highlight of the last 2 weeks for me. So, if nothing for you guys, I'm having a blast.
I'm having a great time too. And for all of you guys that don't know this is my first semester as an SI leader. So this is also my first time holding an SI exam review. And honestly, you guys are making my night so much better because I was so scared coming into this with you guys because I was like, oh my God, they're going to think I'm stupid.
Chris vouched for you, so Chris vouched for you a lot, Katrina.
Thanks.
You're the best.
It's okay. I was salty at Rosemary because she left for the semester that I took Orgo to. She left for the singular semester that I took Orgo to. And I was like, wow, okay. Everybody talks so much about Rosemary being the best, and then she just leaves me when I need her.
It was so bad because Chris literally told everybody that I was going to be their SI leader. And I was like, just kidding, guys. I won't be here.
He literally told everybody.
People literally found me on campus and they were like, why'd you quit? And I was like, I don't know. What? But I'm back, so it's okay.
Okay, guys. So, yes, the answer to this one is the one that you guys see here, the blue one. I don't know why I said that. Okay, so basically the way this is working, we see that we have an acid, right? So that means we are going to cleave tertiary, primary, secondary. On the left side, we have a secondary, and on the right side, we have a primary. So that acid is going to go ahead and attack our CH2, breaking the bond between the carbon and the oxygen. So the one that gets the oxygen from our epoxide is the left side. We are adding on our 18OH to the right side. OH on the left, and then the 18OH on the right. Okay. Onwards. Combo breaker. 3 players just dropped their answer streak. No, guys. No. All right.
Oh, okay.
And this is the most disappointing part of my night. I am out of coffee. Wow. Okay, Rosemary, I see. Flexing on me. I see. I see. That's fine. That's fine. I gave you guys a lot of time for this one because I know that like sometimes it's hard to read the small tiny print.
Maybe.
Yes, this is being recorded, so if you guys have to leave, no big deal. Go ahead. You can head out. Don't worry. And we're going to try our best to get this on YouTube, but no promises on how fast we're going to be able to get it up. Bye, guys. Thank you for coming. Okay. I'm going to go ahead and just end this one, guys, because actually I'll end it at 20 seconds. I feel like I gave you guys a lot of time. Okay. And end. Okay. So the answer to this one was 3 because remember we are in excess HBr, meaning we can either form one side with a Br and then an OH, or we could keep going and replace both alcohols with a, well, we could replace both sides with a Br. Okay. Angel, true. True.
I feel like people who are watching it now are just sitting there thinking, what the hell is going on?
Me.
Tis me.
These questions are from his practice problems. Yes, this is from, these first guys are from 11 and 12 practice problems. And then the parts that I have for 13 of the Diels-Alder reactions are from his lecture PowerPoint. I will stop this one at 100 seconds because I feel like a lot of people are already answering in. So you guys got 60 seconds to answer. And guys, if you guys are on my SI page, most of these are from previous Kahoots that I already did. So the answers of like how the reaction mechanism takes place is underneath a file on my page that says Kahoot answers. Well, it just says Kahoot. And then it should have most of the answers. The only ones that aren't up there is chapter 13 one. So yeah. All right, I'm going to end it in 5 seconds. Okay. There we go, guys. The answer was 7. The answer was 3, and the reason why it was 3 was because it's trans 2-butene, so you need to keep in mind that our CH3s at the end need to be trans to each other. So as you guys can see, the difference between 1 and 3 is that the CH3s on 1 are cis to each other, and then the CH3s in 3 are trans to each other. Okay. Jillian has taken the lead.
Look at you.
Thank you, guys. Yes, ethers can only be cleaved in acid. It cannot be cleaved in base. So this is false. Okay. All right, let's keep going. I think we are not even like 10 questions. Okay, so yes, it is both a strong nucleophile and a strong base. So I don't know why this thing's so laggy. There we go. All right. Olivia, at least it's giving you anxiety now and not on the exam. So if you see these problems show up in the exam, at least you're doing it here and you'll be like, yeah, I remember that one from that Kahoot. That's right. All right.
Kahoots are so much. Like, they get so aggressive sometimes.
I mean, technically, it's not like this fast on the exam because you could go at your own pace, but I kind of put the timing on how fast you guys should be able to get through the problems. Relatively. So this is 30 questions in 30 minutes. So this is pretty fast paced, but some of them are very conceptual, so I give you guys like a short period of time to do them.
Right.
But this one's a little bit harder, so I gave you guys plenty of time on this one. All right.
Okay, so someone said they don't get this one. Basically, it's a multi-step problem where you're going to take the alkene and react it with a something that has an O3 in it. Wink, wink. And then you react that with an acid. So, there's your hint.
I feel like a lot of people left, and that's why we don't have so many answers coming in.
Condensed formulas are the worst.
That's why I hated going into Orgo 2, because in Orgo 1, they gave you bond line, and you needed to know bond line, and then Orgo 2 is just like, yeah, psych, condensed formula it is. And yes, Jessica, peroxy acid. We are reacting an alkene with a peroxy acid to form an epoxide as our first product, and then we are reacting it with an acid. So we are doing acidic cleavage of an epoxide. And that is why our answer is C here, because we are attacking the tertiary side versus the primary side. So the OCH3 goes on our tertiary one, and then the OH ends up on the other side. Okay.
And Olivia, I'm so proud of you. This song is dedicated to you.
Are you playing One Direction right now? I don't know what's worse. Is it the fact that I knew that so fast?
Okay, there you go.
All right, so yes, NABH4 is a weak reducing agent. So it will only be able to reduce our ketones and our aldehydes. It will not be able to reduce our carboxylic acids or our esters. All right. Jillian is still in the lead. Whew. Sorry, guys, this one's lengthy. And I didn't give you guys a crap ton of time.
Same.
I know.
Same.
Retweet.
Dude, okay, I'm gonna tell you guys.
Yeah.
I don't know why I called you guys dude. That was unprofessional, but like this is new. So, funny story that I'm gonna tell like 43 people. When I took my final exam in Orgo 2, he like something had happened our semester and he like completely changed our final exam, so it looked super weird. And literally every single question was either condensed formula or it was phrased really weird. And I literally opened it up, I looked at it, I looked up and made eye contact with Dr. West and started bawling my eyes out. And he literally tells that story every semester where he's like, yeah, I made someone cry, and then looks at me, he's like, but I won't do that to you guys this semester. And I'm like, why do you do that? So, lies. No, for
It's okay. I used to sit in like the third row in his lecture when we had it in person, and he straight up made eye contact with me every single time I looked up, because I'm one of those people that needs to draw structures in the air. So I would draw like lines in the air and he'd just be staring at me the entire time. And I'm just like, Dr. West, I'm not cheating. I'm just confused. So guys, C is the answer here because that is a ketone, and we're doing a reduction with NABH4. A ketone and NABH4 will give us a secondary alcohol. Okay. Next. I'm sorry I'm speed running this, guys. I know everybody wants to leave, but we have so many questions we have to go through.
Plus, we're having a fun time. We're cool gals.
Rosemary, I kid you not, when he used to give my friends and I looks because we would be laughing during the entire lecture, and he would just stare at us.
Okay, as a student, I didn't talk to anyone because I just didn't have any friends in Orgo. But that's besides the point. So afterwards, when I was an SI leader, I would just like go sit amongst the students, you know, like socialize, but like respectfully, right? But I had one student once, I'm just sitting there and he like taps me and I turn around and I'm like, yeah. And he's like, so, theoretically, it wouldn't be that hard to make meth, would it? And I was like, and I started laughing so hard, and Dr. West looked at me like, what the hell? And I was like, I just had to this kid be like,
no way.
To this kid, I was like, that's a funny joke. Drop it now.
Oh my god. Theoretically, you look crackhead. Oh my god.
No, for real. I was like, bruh, this isn't Breaking Bad. Get out of my face.
Is it? Okay. So yes, guys, the answer to this one was A, because that is just an alkene. We are not reducing an alkene with anything. The rest of those guys are carbonyl groups. So yeah, okay. Andrew has hit a streak. Speedy Turtle is in the lead now. So when I took Orgo Lab, I had the amazing Paul Slawick. I don't know if you know Paul, but I love Paul. Paul is my man. He is the reason why I am a SI leader right now and a tutor, because he was my faculty reference. So basically we were talking to him, and yes, Ariana, I love Paul. If you ever talk to Paul, tell him Katrina says thank you, and that she needs his phone number again because she needs to reapply for the semester, and I do not know his email address, and I forgot his phone number because I lost that piece of paper. But basically, he was talking to us about how you treat alcohol. Like, if you end up drinking too much alcohol, how you end up counteracting that. And he's like, you basically treat alcohol with more alcohol, and that's how you end up sobering a person up. And I'm like, well, okay then. Science. I'm sorry.
Guys.
Okay. Oh my god, I totally skipped over that one. I don't remember what the question was. I'm sorry, guys. I'll go back on that one. I'm sorry, Jessica. I think I probably answered it in the Kahoot thingy online. So.
Also, I've realized that we're kind of going through this in a weird way. So I know I'm going to regret saying this, but tomorrow I will record like me going over these answers just like a little bit more slowly, just so you guys get the explanation in order in case you missed it or it went too fast or something like that.
Okay, so that's a great point to bring up. Does anybody that goes to my SI sessions, would you like me to just dedicate the next SI session tomorrow to just going over these problems? If you say yes, I'm not going to be offended. Just know that the chapter 13 ones, we're not going to cover the Diels-Alder reaction. We're just going to do whatever practice problems we have in here. If you guys are cool with that, that's what I'll do. Okay, cool. Cool. Thank you, guys. I answered my question. Yeah, we'll do a tiny bit of the Diels-Alder. So at the end of this Kahoot, there actually is Diels-Alder reaction mechanisms. So I'll show you guys how to do those at the end. Oh my gosh, we're running out of time. Well, we're running way over time. All right, so I'm going to go ahead and hit skip at 10 seconds. Dimerization. Rosemary, do you ever remember seeing one on the exams that had dimerization? Because I don't think he ever did that for my exam.
I have a practice problem like that, but he doesn't ever put it on the exam.
Yeah, it doesn't show up. So don't worry about it. Okay, the answer to this one was C, and that's because we have this CO2H group at the end, which just indicates it's a carboxylic acid. Remember, Grignard reactions are strong nucleophiles and strong bases. So since we have something acidic there, it's going to react with that, and we won't have it. Okay. Next and onwards. He will give you quite a few. He might give you like 3 questions on resonance. So definitely just know how resonance works, because Dr. West likes to put that stuff on there. And these, okay, I think we're in chapter 13 now. So these questions, you guys don't have a lot of time to answer because I felt like you guys would be able to fly through them pretty fast. So I'm sorry ahead of time. Don't hate me. Okay, so the answer to this one, yes, you guys are right. It is 3, and that is because we cannot turn a CH2 into a CH3 in resonance. That is not how that works. It is just charges, radicals, and electrons that change. We do not form another hydrogen. Okay. Andrew has taken the lead again.
But Speedy Turtle is coming for you.
Speedy Turtle is right there. Speedy Turtle actually kills it in Kahoot games when I do the weekly Kahoots. I don't know if it's the same person, but like Speedy Turtle ain't so slow. Yes, guys, this one is false. A more conjugated molecule will have a higher wavelength, but a lower energy and lower frequency. Please remember that. Okay. This is the ones that I told you guys are awful because, yeah, this is a lot of reading, and I don't do reading. You guys should know this about me. When I take exams now, my brain is so brain dead that if like the question is longer than one sentence long, I zone out and I have to read it about 3 more times for me to understand what it's asking me. And it's horrible because I'm taking genetics and all the questions are really long. So I'm like,
wait till you start studying for the MCAT.
Rosemary, don't bring that into my life right now. Okay. All right. So guys, yes, remember, it says equilibrium, and it's asking which one it will yield predominantly. A equilibrium controlled reaction will form our thermo, aka our most stable product. Yes, I am with Dr. Vininger. I had an exam today, and and right after that, I had to help, Rosemary and I had to figure out how the heck we were going to do this exam review. So, you guys want to know how my day went?
One time, someone told me that we apparently seem very put together and organized, and I've never been so shocked, but also happy and flattered, because behind the scenes, we are a hot mess.
Oh, yeah. You should see our text messages. All right, guys. So the answer to this one is B, and that's because we don't split up the double bond to give us 2 radicals. They will move together as electrons. So we do not split a double bond into 2 radicals. Okay. Onwards. Genetics. Okay. The only reason, to be perfectly honest with you guys, I'm not gonna lie to you guys. The only reason I loved Orgo 2 so much was because I, 1, had it in person for the first half of the semester, and 2, I was taking Orgo Lab with it. So whenever I would fail an exam in Orgo Lab, I would do great on the exam because I actually learned how to do, oh my god, I cannot believe I did that to you guys. I am so sorry. I'm so sorry, guys. As you guys can see, my brain was dead when I made this one. So the allele cation has how many pi molecular orbitals? Who's gonna say? Yes, guys, it's going to have 3 pi molecular orbitals because I'm just asking about pi molecular orbitals. I'm not asking for pi bonding, pi non-bonding, or anything. It is just pi molecular orbitals. I'm so sorry I did that. I will show you guys the real question eventually. Oh my god.
I just had the stupidest moment of my life today. I just read this message, I'm an animal person, and I just sat here and I was like, you're an animal person? Like, you identify as like an animal? And it took me like a second, like 1 too many seconds.
Okay, guys, so an allele radical has how many electrons in the non-bonding pi molecular orbital? We are just talking about the non-bonding pi molecular orbital, and we're talking about the electrons. There is 1 electron because we have 3 electrons in total for the whole molecule. Okay. Onwards, onwards, onwards. Like I said, guys, these are easy questions that Dr. West could be asking you guys. Who is sleep mood? You guys should have heard Rosemary and I having this conversation on how we were going to do this exam yesterday. We were literally on the phone for an hour and we didn't even talk about the exam that much. We were just talking about how life was going. And now we're just like, yeah, I'm done. I'm done. Okay, so this one, yes, it says intermediate reversible reaction. Please know something. Even though it says that the less stable product is still forming more rapidly because of the activation energy. So the less stable product is still forming faster. It is not talking about which one is going to be predominant or any of that. I will explain this in better detail tomorrow, but yeah, okay. Keep going. Andrew, you are killing it, and you were one of the people who was just like so nervous about the exam. You'll be fine. You'll be good. I have full faith in every single one of you guys when you guys take this exam this week because you guys are honestly all the material I've thrown at you guys have been crushing it. So I don't know. Okay. So the allele radical has how many pi bonding molecular orbitals? We're talking about pi bonding molecular orbitals. So the allele radical will only have one pi bonding molecular orbital. It will also have one pi non-bonding and one pi anti-bonding molecular orbital. Okay. I'm still surprised we have 32 people in here.
We're
If I'm
so
being
entertaining.
honest. Yeah, that's it. That's it. Okay. Guys, this is false. Hold on. This thing is like so messed up. Okay. I'm asking about pi bonding, pi non-bonding molecular orbitals. Racemake. Andrew, there was one question in there that I was already talking about the cleavage reaction. I'll go over it into more detail tomorrow. But yeah. So 3 pi bonding non-molecular orbitals. We are looking at non-bonding molecular orbitals. It only has one non-bonding, but it has 3 pi molecular orbitals. Okay. President's just having a fun time in the chat right now. Okay. And now we are at the Diels-Alder reactions. I'm so sorry to throw these guys at you at the end, but I know we didn't cover a crazy lot.
Also, it just occurred to me that I didn't give you guys a heads up. I have a bird, so there's not a child screaming in the background. It's a bird. I forgot to mention that.
Not a child.
It's scared.
Daphne.
She's a bitch.
Rosemary.
I'm so
Come
sorry.
on. All right, guys. There's not much time left on this one. So basically, look that our dienophile, the alkene, is in a trans location. So you know that our molecule at the end needs to have 2 trans molecules. The only ones that are left when we look that the molecule needs to be trans at the end is 1 and 4. Then from there, you can choose which one based upon, am I saying this right?
So,
What am I trying to say?
So basically, you know that you have, first of all, you don't have a double bond in the bridge, so you automatically get rid of 2 and 3. And then you see that the 2 are trans, right? So the 2 carboxylic acids have to be trans to one another. So 1 would have them trans, and 4 would have them cis because they're both pointing down. So 1 would be the right answer.
Guys, I'm so sorry. I don't know why I put the answer choice D. But yes, it is A. That is my bad. That is 100% my bad. But the answer is A. I'm sorry. And yes, so these guys, they're asking if they're going to be considered endo. 1 will be considered exo, right?
No. So endo and exo are only when... Sorry. No, this is honestly I learned like kind of recently. So, well, anyway. So they both have to be pointing up or down to be considered endo or exo. If they're trans and they're opposite, you can't pick endo or exo because it's going both directions.
Okay. Makes sense. I hope that made sense.
But sorry, someone said, so would 4 be exo? No, 4 would be endo, and that's because they're pointing down towards the double bond.
Both the diene and dienophile have to be in the same direction. So I just keep hearing that bird. The diene and dienophile. So remember, the dienophile is what that group is coming from. So basically, the yeah, go ahead.
So what he meant was, when I said pointing in the same direction, what I meant by that is the two substituents. So on the dienophile, we have those two substituents. If they're both pointing up, or if they're both pointing down, we can call it endo or exo. But if they're trans to one another, you can't call it endo or exo. So we weren't talking about the diene or dienophile, we were talking about the substituents.
And then somebody asked if 2 would be exo. Yes. Oh, wait. Would 2? Yes, 2 would be exo, and it's because both of them are cis. They are cis, right?
But it's, okay, so yes, but also no, because there's a double bond in the bridge. So that would never happen, and it would be complicated, but if there was no double bond in the bridge, yes, 2 would be exo.
So guys, if you see a double bond in the bridge, no, we won't be able to do endo or exo. Only if we just have the singular double bond. Karina, have a great night, and thank you. I'm glad we could be of some entertainment to you.
You made my week, so I heart you.
Okay. So this is reverse synthesis, guys. Retrosynthesis. I don't know why I said reverse synthesis. This one's kind of complicated. I always hated this one. I feel like it's so much easier if you could draw out these molecules, and I think that's what makes it worse when you have an online class, because you can't draw like directly on the exam. So like, yeah. Yeah, I'm sorry guys. I know it would be so much easier if you could just draw on the paper, but like you can't, which is a pain, but. I don't know what was on the extra credit, to be honest, because we're not allowed to view that stuff the way that Dr. West has it set up on his page. But if it seems like stuff that's like this, I would say yes. But things having to do with exo and endo, I don't remember ever seeing that on the exam, so yeah. We still have not held a meeting with Dr. West, but based off of his emails, he seems pretty set on his 50-minute thing, and I think somebody over the summer might have ruined it, and that's why he keeps it at 50 minutes. So I'm so sorry, guys. Okay, so yes, guys, this one's going to be 12, because if you look at it, I said 12. This one's going to be 4, and that is because our molecule is in the S-cis configuration, and then our dienophile will have that CO2-CH3 group and that double bond there. So when we form that crap, we're gonna have that double bond form another cyclic compound, and we'll have the CO2-CH3 group on there. Okay. Yeah, I'll explain that one in SI tomorrow. I'll mainly focus on the Diels-Alder reactions tomorrow because we didn't get to do much of that. So yes, I will explain that in SI. And if it makes you guys feel any better, I have a biochem exam this Friday that I haven't really studied for. So you guys are probably better at Orgo 2 than I am at biochem. So to be fair.
When I took biochem, it was my first semester doing SI, so I was friends with the SI leader for biochem, and I would literally, I had so much going on. I would come into the session and sit in the front row, and I'd be like, Thomas, don't talk to me. I'm just going to sit here. Don't ask me questions, just let me be. And he was like, oh,
okay.
Thanks.
Thank you, guys. All right, so the answer to this one is D, and that's because if you look at it, we need our two compounds that were the two substituents to be cis to each other because that is what they look like in the starting product. And you know that now you're choosing between 3 and 4. And basically 3 can't be it because we don't have an S cis in our diene. We only have that one single bond. And guys, I would give up all my time to give you guys a good exam review because I think, like, I know a lot of people find orgo to be one of the most challenging things before. Like, I know going into orgos, I was like, oh my god, this is what's going to end up, like, killing me. This is why I'm not going to be able to get into medical school because I'm not going to understand orgo whatsoever. So, like, that is why I totally understand the fear of orgo.
Yep.
Rosemary, was it not the same for you? Like, you went into orgo thinking it was going to be this huge beast that was just scaring the crap out of you?
Honestly, so I was a psych major, so I didn't do, like, any chemistry, and then all of a sudden, I did orgo. I don't really know how this happened, but I was just like, oh, whatever, orgo, I don't even know what that is. And then I sit down in my first day of class, and the girls next to me on either side are talking about how they failed twice. And this was, like, their third time, and it was the worst thing in the actual, like, ever. And I was just sitting there, and I was like, I'm never gonna be a doctor.
Mood. Honestly, this class gives me anxiety, too. I have anxiety for you guys. If you guys ever want to know, when you guys are going into the exam, I'm sitting there and I'm stressed.
For exam 1, Katrina and I are literally sitting there texting. He's like, I hope they're doing okay.
Okay, so it's asking what would be the best synthesis. So guys, as you guys can see, they're both pointing downwards. So in this case scenario, yes, you could call this endo. If you guys want to know endo versus exo. So they're in the same direction. So you need to know that the molecule will be cis. So that means we can only choose between 2 and 4. 4 won't be it because that is a bicyclic compound. That's not, you're not gonna use that to create that molecule. I'll go into more detail tomorrow, but yeah. What was I gonna say? Okay, so to be perfectly honest, the reason why I became an SI leader was because in Orgo 1, I failed the first exam after thinking I was gonna do great on it. I literally went into the first exam and I was like, yo, I'm gonna do so amazing. I got my score back and I was like, so I think I'm going to drop out of OrgoChem and just change my major to business. I was literally thinking about switching my entire major because of OrgoChem and failing the first exam. So then I was like, yeah, I should go to SI. And then I started going to Chris's SI and I was just like, oh my God, Orgo makes sense. This isn't bad. So literally my encouragement to become an SI leader was from that. Chris is top notch, A1 right there. And if you guys want to know, I do better in chemistry classes than I do for biology classes, and I'm a bio major, funnily enough.
Same.
I was like, maybe I should have just become a chem major.
Me too, and then I heard about PChem, and I was like, no.
Oh yeah, I was like, PChem, hell no. Okay, so guys, we can do a Diels-Alder reaction mechanism for this. And the reason why is because we have a single bond between our 2 double bonds. So we can rotate that. So once you rotate that, you can form your molecule, and that will give you the really ugly compound of D. Wait, scratch that. B. Yes, because you're forming this bond between the 2 of them. Yeah, I'll explain that in detail tomorrow.
Wait, I have a really quick way to make this super, super fast and easy,
Yeah.
right? Okay, so you have 3 rings in the starting material. So you have to have 4 rings in the product. So automatically 2 is out, right?
Oh my God. I put the wrong answer for this. I'm sorry, guys.
Oh.
That was my bad.
But then the second thing is you have that 5-membered ring. So 1 and 3 are both out because they have a 6-membered ring at the bottom. So that's why D would be the correct answer.
D is the correct answer, guys. So you guys were all right. I'm sorry. I don't know what got into me yesterday when I was making this. Rosemary and I were literally on the phone, and I think my brain just exploded because I had biochem that I was studying for at the same time. And let's not mix orgo and biochem together because it never ends well. But yes, you guys are right. Okay. The answer is 12, yes. The answer is 12. You guys can see how little sleep I get. I run on coffee.
Same. There's no blood in my body. It's all caffeine.
Straight caffeine. And then when I don't have my caffeine for the day, I get the worst headache. So if you guys ever see me in SI and I'm just like this, it's because I didn't have any caffeine for the day. So this one is D, and that's because did I mess with, I don't think I messed this one up.
Okay. So
this was the one you warned them about.
Yeah, wow, I just had like a mini stroke. Anyway, so when I was talking about the tert-butyl thing, if it looks like 3, those tert-butyls are way too bulky. They can't rotate and do the reaction.
Yes, exactly. Andrew actually sent it to me privately. He said 3 was wrong because of sterics. Yes.
Yeah. And then for for 1, 2, and 5, none of those are conjugated. So that's why none of them can undergo it. And D.
Andrew's asking if that's only for tert-butyl. I think it's just for like, yeah. Okay. All right. Let's keep going. Oh, that's it.
Yay!
In 3rd place, we had Jason. In 2nd place, we had Jen. And in 1st place, who took it? Who took it?
Andrew!
And guys, originally I wanted to give you guys a prize for this, but apparently I wasn't allowed to do that. But if you guys want, if you guys go to the Boca campus, maybe at one point in time, I could give you like guys like a goodie bag or something. If you guys wanted just like a bunch of sweets, I could totally do that. Just,
Or
let me know.
You could just send me your address and I'll send you a bag of glitter. That's a joke. Don't send me your address.
I was like, I don't think Andrew wants a bag of glitter. All right, guys. I hope that was fun for you guys. But yeah, good job. I'm proud of you guys. You guys are going to kill on the exam, and I will see you all tomorrow. Please do a bunch of review questions, okay? And yeah, I hope you guys have a great night. Thank you for coming and staying so long.
Thanks for joining our shenanigans. Have a good night.
Oof, all that beeping.